So our next speaker is Joseph Orr, who gives a talk entitled Angle-Monotone Path in Non-Obtuse Triangulations.
Thank you. So this is a happy melding of Anna Lubia's interest in all kinds of paths, just like in the previous talk, and my own interest in unfolding polyhedra. An angle-monotone path is a path that fits inside a 90-degree wedge or cone. It's characterized by an angle which I'll call beta. So here beta is at 45 degrees and plus or minus 45 around it. The curve falls inside there. It falls inside that if you move that wedge to each vertex. And if the lower ray here is the x and this is the y, then it's xy-monotone. We consider these wedges to be closed. So the main result here is a reproving of a beautiful theorem of Dehkordi, Frati, and Gudmundsson, which I'll read and then translate into our notation. For any Gabriel triangulation of a point set, for every 2 points there exists some angle such that G contains a theta path from S to T. And the way that we're rephrasing this is in any non-obtuse triangulation, every pair of vertices is connected by an angle-monotone path. So we just require the triangulation to have no obtuse angles, so that's what non-obtuse means, and that's implied by a Gabriel triangulation. And every pair is connected by one of these paths, 4 different angles. So this is what they proved, and we're reproving it in a different way. So here is a picture that explains a lot of what we're doing. This is a non-obtuse triangulation. And here's a point S that's the source. And if we set beta to be 45 degrees here, then this is the set of all paths, angle-monotone paths, reachable from S. And it has a lower boundary, or clockwise boundary, and an upper boundary, or counterclockwise boundary. And for example, if you look at here, this edge falls in the wedge, this edge falls in the wedge. This is a little below the axis. This is a little to the left of the y-axis. So these blue edges are not, but the red edges are in. So our main idea is to study the properties of this set, and imagine rotating beta continuously around and then connect everything to S. So these rays here at the boundary are just a technical trick in order to simplify the proof, and I'm not going to spend any time on them. We proved it without that, and then it turns out to be simpler to add this in. Okay, so some notation. We'll call R of beta is the whole region, the geometric region, between the lower and the upper. And this is an angle-monotone path, and this is an angle-monotone path. One other thing, the upper path does not contain any edge parallel to the lower ray, because these wedges are closed, and if there was an edge parallel to the lower ray, there would be an edge completely vertical also, and that would be chosen for the upper path. So within this wedge, the first important result is that every vertex is accessible in that whole region. No vertex is inaccessible in that region. And here's the rough idea of a proof. Imagine that there is some inaccessible vertex in the region. Call it V, and let's say it's the leftmost one in this orientation and the lowest. So this is inaccessible by an angle-monotone path from S. So look at this segment S to V. If that's an edge, then of course this is accessible. That would be a contradiction. If this is not an edge, rotate this S about V until you bang into some edge, which you'll have to do because this is a non-obtuse triangulation. And then you fall in this negative wedge. And now look at U. It can't be inaccessible because this was the leftmost inaccessible. And since this is accessible and it's in this reverse wedge, then it fits in this other, in the positive wedge, and that contradicts the assumption that this was inaccessible. And there's one more case which I'll leave out, but everything in this, every vertex between L and U is accessible for one fixed beta. And now let's start to think about several different betas. And imagine aiming toward rotating beta continuously, but of course we'll jump to the next critical beta rather than rotate it continuously. So here you see beta 1 and beta 2. Beta 1 includes, it would be at 45 degrees, and beta 2 would be straight vertical. And we want to look at how the two sets that are reachable for these two adjacent betas, so to speak, in this discretization of the continuous rotation relate to one another. And in particular, we want to look at how the upper end of beta 1 relates to the lower end of beta 2. And the important lemma here is that the upper path in beta I is a path in beta I plus 1. In other words, they overlap. So if you go here, this purple curve, which is the upper one of the beta 1, is a path in beta 2, so that there's overlap. And if you then join these two regions together, we want to argue that no vertices are orphaned between them, so that as you move to the next beta, you're covering everything. And that is true, and the rough reason it's true is that the upper path never includes an edge along the lower ray, and when you rotate beta, so to speak, you drop things out of the bottom, but not, you can't destroy it, and so that the two overlap, and there's no vertices orphaned between. So therefore, in a non-obtuse triangulation, every pair of vertices is connected by an angle-monotone path. So that's the reproof. Now, we wanted to go on and try to prove that there's a spanning tree from every S. So what we have established is that there's a spanning graph. From S, we now can cover the whole thing, and it's a spanning graph. And within any, for a fixed beta, this is again the same picture, you could delete every, for every vertex that has more than one incoming edge, you could delete an edge and turn it into a spanning tree. So this is now a spanning tree where I've deleted this edge, and this edge, etc. So you can get a spanning tree in here, in one of them, and now you imagine rotating around and getting all the vertices in the spanning tree, and that seemed positive. We worked just for intuition on graphs where all the edges are at 45 degrees, 90 degrees, multiples of 45 degrees, and we're able to prove the spanning tree there, but it turns out it's not true. It's false. We found an example where from S, there is no spanning tree of angle-monotone paths, but rather you are forced to get a cycle. And I'll explain this a little bit and then move on. So in this picture, let's say if you look at F, there are exactly two ways to reach it from S with a wedge, imagine here. You can either go down or up. So I just showed one. And that's true for C, D, E, and F. But A and B, you can't see it here, but let's see, in the next picture, there's circles here that are illustrating the construction. We move A and B a little bit toward each other so that you break the ability of having exactly two paths, and there's in fact just one path to reach A and one path to reach B. And that would be this, let's just concentrate on A, this dark blue path here from S, A, X, A. That works. But if you try to go this way, you just miss. You can't quite see. The color is washed out. But the wedge, this opens up a little bit too much and you can't reach it there. So the only way to reach A is the blue path. The only way to reach B is the red path. And you've created a cycle here. So you don't have a spanning tree. So that's a shame, but at least it settles that. Although I guess it's possible that there always exists some S from which there's a spanning tree, but it's not true for every S. The next result moves us towards unfolding of polyhedra in that we were able to show that there always exists a boundary-rooted spanning forest for any non-obtuse triangulation. So this is a non-obtuse triangulation, and now take trees rooted on the boundary and span everything inside. And this turns out to be relatively easy to prove. You break up, take any vertex here and break it up into quadrants, quadrant 0, 1, 2, 3. And then within each quadrant, let's say this quadrant here, that you're just going to find the angle-monotone paths from here to the boundary. You take every vertex, take any vertex, and start growing a monotone path until you reach the boundary, or you reach a tree in the forest so far constructed. So, for example, here you would grow and you go out to the boundary. Then for this point, you grow and you hit the tree, and so you just join it. And you continue in that way, and this will span the whole graph. And as I said, the algorithm is quite simple. For each quadrant, take the 45-degree angle appropriate for that quadrant, grow a path from every vertex until you hit the boundary or hit the forest, and just grow all these forests, and you get a picture like this. Now, the reason that I was interested in this is because I see an application to unfolding. And we made a conjecture in our paper that every acutely triangulated, so this is a little stronger than non-obtuse, every acutely triangulated convex cap that is nearly flat, I'll explain that in a second, has an edge unfolding to a non-overlapping polygon in the plane. I'm going to show you a picture of this. So this is what I mean by a convex cap. It's like the top of a convex polyhedron. Nearly flat means that if you take say the z-axis as the purple vector and look at the face normals to all of these, they're not that far spread apart. Or rather, to be more precise, the face normal is bounded by a sufficiently small angle, sufficiently small from the vertical. So this is, you can recognize this as a boundary rooted forest spanning this. And now you just cut all of these lines, and it unfolds to a simple polygon in the plane. Here's another view of it. And then here is its unfolding. And you can kind of see this now. So let's see. So this long path here opens to this gap here, etc. So you can see all around. And so after we wrote this paper, I worked on this, and so I was able to prove this. And I've written a report on it, and here's the high-level idea of the proof. Take the convex cap, project it down to the plane. With the affine triangulation, when you project, there is some flatness, or there is some bound on the flatness such that when you project it, it remains acutely triangulated. Apply the boundary rooted forest algorithm, find that, lift it back up onto the surface. That's what I was showing you. And then the hard part is to prove that this opens up and there's no overlap, and so you get a simple polygon in the plane. And so that's the result of this picture. And I've implemented it, and of course that this is not nearly flat. This is very far from flat, but it still works. But I can only prove it for about a very small, nearly flat. So thank you very much.
We have time for questions?
Have this image of a big hand coming down and crushing.
Absolutely, yeah. Yeah. Well, I should say that I think the community has thought something like this was true for years. I remember thinking about this 20 years ago. But so it should be true without the assumption of acutely triangulated. So that I needed, because I needed the non-obtuseness in the plane and the, et cetera, et cetera. But this is surely, well, no. Nothing is sure. It seems like this should be true without the heavy assumption of acutely triangulated. Yes, Art. I've been working to try to make a counterexample, and I have not been able to do that. It depends on how acute. So for example, if no angle is greater than 87 degrees, then I think the normals have to be within 5 degrees. I've computed bounds, explicit bounds, but it depends on the slack of the acuteness.
So does the normal need to be good enough for the vertical projection?
Yes. So I need the vertical projection to be non-obtuse. So that's why, so if you give me, let's say, 3 degrees of freedom in the acuteness, then I have to flatten it so that it still stays acute or non-obtuse, so that I can apply the algorithm and then lift it and then do the work in 3D. Yeah. Yes, Stefan. Oh. Yeah, just cover with. Right, but the curvature here has to be quite small. It's a constant, yes. Oh. Would you like to co-author a paper? No, I think you're absolutely right. This is quite new, and I've been mainly trying to extend it without the acuteness, because I just don't think that's necessary. So there are several tools that I use that do not need angle-monotone chains. I need something called radially monotone, which is much looser. And so the core of the proofs don't rely on that. It's just the projection and lifting that I needed. So. Thank you.